So, hello and welcome to this lesson in our study of optimization 2. This happens to be the seventh lesson, and we'll be talking about sensitivity analysis. So, if you could recall, in our sixth lesson, we spoke briefly on this and later discussed the duality, right? So, in this video, we'll be going much into the sensitivity analysis. So I'm Guido Cranwinoff, a final year student of mathematics at KNUST. I'll be taking you through this lesson. Don't forget to subscribe to the channel for more videos and like the video if it helps you, okay? So I told you this that after a linear programming problem has been solved, alright, it is useful to study the effect of instantaneous changes in the parameters of the problem on the current optimal solution. So for example, after solving the linear programming problem, one may find out that certain values of the variables have changed, and therefore would like to know whether the current optimal solution is still optimal under the changed circumstances, or else he wants to know how far the input parameter values can vary without causing any changes in the optimal solution or the composition of a basis set. Such an investigation is known as sensitivity analysis or post-optimality test in linear programming. So as I told you, maybe we can have this question: maximize z equals 6x1 plus 2x2 subject to the constraint x1 plus 4x2 less than or equal to 14, and let's say x2 plus 3x x1, let's say 2x1 plus 3x2 less than or equal to 20, and x1 x2 greater than 0. So let's say we've solved this problem, right? And now we have an optimal solution. So we would want to know how, when this what that we have here is profit and it's kind of change, right? So if it changes, we would want to know if the current optimum solution we have will still be optimum for instance, when let's say we have 7 here and we have 3 here, or what if the right hand side also changes, because they are what resources. So this can also, maybe let's say we can lose a machine and now we'll just be having 10. Maybe let's say this can represent labor, we might employ more labor, you might have 25 here. We want to know the range for which the current optimal solution will still be what valid when these changes are made, okay? So that's what sensitivity analysis is about in linear programming. So some of the questions we ask ourselves is: what happens when the resource availability is curtailed or increased? We also ask ourselves: what happens if a new activity is added or if an existing activity is deleted? So take note, the strength of the simplex method is that the final tableau gives answers to some of these specific post-optimality questions, okay? And that's what we are going to do in this video, so don't worry, the understanding will come. So the purpose of sensitivity analysis is to know the effect on the optimal solution of an LP model due to the variations in the input coefficients, also called parameters, one at a time. So I told you the input coefficients here are this 6, 2 that you can see here, 14, 20, 2, 3, the force, okay? So sensitivity analysis provides the sensitive ranges, both lower and upper limits, within which the LP model parameters can vary without changing the optimality of the current optimal solution. Yes, I really want you to understand what it's about before we go into solving questions, so that you understand the meaning of the values you are going to get, okay? So take note, it says it provides the sensitive ranges, both lower and upper limits, within which the LP model parameters can vary without changing the optimality of the current optimal solution. Okay, so let's take an example. We have an example here. So we have a problem here, and note the original LP problem is called the primal problem. So it says maximize z equals 3x1 plus 3x2 plus 4x3 plus 7x4 subject to these constraints. Okay, so when we solve this using our simplex algorithm, this is going to be the final simplex tableau, right? So you can see the question said we should what maximize, and all our CGs minus ZG are less than or equal to 0. So an optimum solution is found, right? Okay. So you see from this table, x1, the value for x1 is what? 22 on 7. The value for x4 is what? 41 on 7. So with this question, we had z is equal to 3x1 plus 3x2 plus 4x3 plus 7x4. So we have 3 here. That corresponds to the decision variable x1. You have this which corresponds to x2, this and that. So if any of these values change, if there are changes in them, what will be the effect on the current optimum solution? That is what we try to find out using sensitivity analysis. Okay, so we try to look at changes in the coefficient of the objective function, range of optimality, the range in which still the current solution is going to be optimum. Okay, so these changes, we study them by grouping them into two categories. That's the CGs corresponding to non-basic variables, and the CGs corresponding to basic variables. Okay, so you can see that our CGs here, right, we have 3, 3, 4, and 7. But you can see that when we come to the simplex tableau, it's only x1 and x4 from the 4 decision variables that we had here, which are basic variables, and the rest of them, that is x2 and x3, are non-basic. Okay, so to study the effect, we group them into two. We consider those which are basic variables, and then we consider those which are non-basic variables. Okay, so first let's consider those which are non-basic variables. So the non-basic variables in the above problem are, so when you say non-basic variables, it's just the variables which do not appear under the basis after the final simplex tableau. So you can see that we have x1, x2, x3, x4, s1, s2, s3, right? To be, we have 7 variables here, and out of that, these 3, x1, s3, and s4, right? So those are the 3 basic variables. The rest will be non-basic, right? So that's why the question says that the non-basic variables in the above problem are s2, s3, x1, and s3. So by looking at the final simplex tableau, right, we find that if C2 is increased beyond 8 over 7, then C2 minus Z2 will become positive, and hence S2 will enter the basis. And this is going to affect the current optimum solution we have. So this is an illustration. So this is x2, right? And you can see that Cj minus Zj here is minus 8 over 7, right? And this is less than 0. That's the reason why an optimum solution has been found. So if we should increase this x2 beyond minus 8 over 7, right, that means that we are going to get a positive value here, and we'd have to continue with the iteration, and that means that the current optimum solution will be affected. So these are the questions we try to answer in sensitivity analysis. So that means that if we want to look at the range in which we can vary this parameter s2, it won't go beyond 8 over 7. So it says that the coefficients of Cj minus Zj rho in a final simplex tableau for non-basic variables indicate the extent of increase in their respective coefficients of the objective function and still keeping the current solution optimal. If these coefficients are increased beyond this limit, the current optimal solution will change, as I've said. So that means that when we take the second, we can take x32. That means that x32, we can't increase it beyond 9 over 7. So what this means is that when it comes here, this x2, we can increase it, but it shouldn't go beyond 8 over 7. Okay, this one too, we can increase it, but it shouldn't go beyond 9 over 7. So if we increase it within this range, then that means that the current optimum solution that we have will still be what? Valid. Even though there are changes in what? The parameters or the input parameters now. Do you get it? So those are for non-basic variables. You just have to look at the Cj minus Zj column, and the values that you get for them are the extent to which the increase should be what? Limited. So the increase shouldn't go beyond that extent. Okay, if not, the current optimal solution will change. So now let's talk about basic variables. That's the variables that we can find in the basis. Okay, so we can see that in the above final tableau that we had, x1 and x4 were basic variables, and we are interested in knowing the extent of changes in their coefficients in the objective what function. So we consider the basic variable s1, for instance, and define delta 1 as the change in what? C1. So we are considering s1, right? So we represent delta 1 to be the changes in it, right? And we are saying c1 because of x1, c1. So coming. And so we consider the basic variable s1 and define delta 1 as the change in c1. So I think c1 is 3, right? This is c1. You know, it is maximize z equal to, so we sum this. We are starting from 1 to n. C, so let me do this j. So cj and zj, right? So cj is 3 here. So we want to know the change or the range of values this 3 can take, and still our current optimal solution will still be valid. So in order to find out the range for delta 1, we each divide the cj minus zj coefficient corresponding to known basic variables by the corresponding coefficients in x1 row, right? So we are looking for the range for c1, right? So we are talking about delta 1, the change. So we take s1, and you see when you take s1, we take the values here. So you can see we have 1, 5 over 7, 3 over 7, 0, 8 over 7, 0, minus 1 over 7. Okay, and that's what you can find here. Then we take the cj minus zj. So this are cj minus zj, right? So when we take it, then what we do is that we do cj minus zj over x1, right? So here 0 over 1 will give us 0. Then here minus 8 over 7 over 5 over 7 will give us this value here, negative 8 over 5. This over this gives us minus 8 over 3. 0 over 0, we are getting infinity. This gives us minus 7 over 8 dash. This gives us 4. Okay, so now we have to get an upper limit and a lower limit. So always the upper limit is the positive coefficient in the cj minus zj over x1 row, right? And note that if we have more than one positive coefficient, we select the one with the smallest coefficient. So here we have just one, that is this, which is 4. So we select it. So this is going to be the upper limit. So now to get the lower limit, we select the we select among the negative coefficient, the one which has the lowest absolute value. So you can see with the negative value that we have here, the minus 8 on 5, minus 9 on 3, minus 17 on 8. If we find the absolute value, right, the smallest among them will be this, minus 8 on 5. Okay, so we select that. So that means that the change can be between minus 8 over 5 and 4, right? So to get the original values that our C1 can take, we'll have to take our C1. I told you our C1 is 3. And so after you go to the original problem and find the coefficient of x1, which is C1, that is, we would have 3 minus, the lower limit, right? Actually, it is plus, but 3 plus minus 8 on 5 is what? 3 minus 8 on 5. And this is less than or equal to the C1 value, and it's less than or equal to 3 plus the upper limit, which is 4. And when we do this, we have 7 over 5 less than or equal to C1 less than or equal to 7. Right, I think 7 over 5 is should be 1.2, or so 5 here. We can bring 1 here. We have 5, 2. So it's 1.4. So that means we get 1.4 less than or equal to C1 less than or equal to 7. So that means that even though C1 is 3, right, if it still takes any value between this range, still our optimum solution will still be valid. So let's say originally, where's the problem? So let's say originally this is a product that when you sell it, the profit is $3, and now the profit has been increased to $6. That means that since it is within that range from 1.4 to 7, still our current optimal solution is going to hold. Okay, so that's all what sensitivity analysis is about. It's analysis, so you have to really take your time to analyze it very well. Okay, and note that we could do same for what, x4. So you can try x4, because so doing x4, that means here you're going to write the values for x4 here, then to be cj minus zj s4, and use the same decision that we used to get our upper limit and lower limit. Okay, all right. So now let's go to the range of feasibility, that is changes in the right hand side. So to determine the range of feasibility, we divide every coefficient in the right hand side column by the corresponding coefficient in the first slack variable corresponding to the first resource constraint column. So to get the changes in the right hand side, we just change the right hand side. We take the first slack variable and we do right hand side over s1, right? So you see we get this. And what we do is that the least positive ratio, right, indicate the extent by which this resource can be reduced without affecting the current solution. So here the least positive ratio is, we have just one of it, so actually 22 over 8. Also the least negative ratio in absolute value, which is minus 269 on 39, indicate the extent to which this resource can be increased without affecting the current solution. Okay, so for instance, when we take the first resource, where the problem we are solving. So this is a problem we are solving, right? So you see the first resource was what, 9. So we want to know the changes this 9 can also take, and still our current optimal solution will still be what? Will still hold. So it will be 9 minus the 22 on 8, then 9 plus the 26 on 9, because we said this was the lower limit, like the extent to which it can be decreased and the extent to which it can be what increased. And this will give us the open set 25 on 4 and 620 on 39, right? So that means that the resource for the first constraint can take any value between these two numbers, okay? And still our current optimal solution will hold. So this is a second example to make sure you really understand what we are doing, okay? So it says maximize. So we have this LP problem here. So when you solve this, the final simplex tableau is giving us what you can see here. We can see the optimal solution is S1 equals 4 and X2 equals 8. And S3 is 48, right? Slack 3. And the maximum value is 2240. So it says you find the sensitivity range of values for the basic variables S1 and S2 and which the current optimal solution will still hold, right? So to do that, we consider the basic variable S1 and define delta 1 as a change in C1. So we write this table. So S1, which is given, so we just get it from the simplex table. So S1 here was 1 0 minus 1 on 2 1 on 9 0, right? And we also write our Cj minus Zj. Then we find Cj minus Zj over Sj. So this will give us 0 over 1 is 0. Mostly we even write that we're not interested in 0, we're just interested in positive values and negative values. Then 0 on 0, yeah, minus 20 on minus half 40. Then this one is minus 60 and dash, right? So the positive coefficient gives us the upper limit. So here the upper limit is 40. In the negative one, here we have just one negative. But if we see, if there are more than one positive coefficient, we select the one with the smallest coefficient. And here, so for the smallest limit, we select among the negative coefficients the one which has the lowest absolute value. But here we just have one of them, so it will be negative 60. So there's the upper limit and this is the lower limit. So we would have negative 60 less than or equal to delta 1 less than or equal to 40. Then we'll go to our objective function. I'm going to look for the coefficient of S1. That is what? 160. So that means that the changes that value can take will be 160 minus the lower limit less than or equal to C1 less than or equal to 40 plus 160. Right? And 160 minus 60 is what? 100. Then less than or equal to C1 less than or equal to 40 plus 160, which will give us 200. So that means that even though C1 was 160 in this question, it can take values between 100 and 200, with 100 and 200 inclusive, and still the current optimal solution we have will be valid. It will not change. It will still hold. Okay. So therefore, the range of values for C1 over which the solution basis will remain optimal, although the value of the objective function may change, is this. Right? So now doing same for S2, we just have to construct S2, then Cj minus Zj, then Cj minus Zj over X2. So we do this. This will be our upper limit, our lower limit. So we get this minus 40 less than or equal to delta 2 less than or equal to 120. Right? Then we look for the coefficient of X2 in the objective function, which is 200. It will be 200 minus 40 less than or equal to C2 less than or equal to 200 plus 120. And this will be in. So even though C2 in the question was 200, it can take values between this range with the endpoint inclusive, and still the current optimal solution will remain unchanged. Okay. So this is all what sensitivity analysis is about. It's very simple. So we try to look for changes in the input parameter that we have, which will still make sure that our current solution holds. Okay, so if you didn't understand this video, please go over it and trust me, understanding will come. So thank you very much and see you in the next video.